All right, we're talking about matrices. We're stuck in the matrix, like we talked about in class. Let's define a matrix. An m by n matrix is a rectangular array of numbers with m rows and n columns. Okay, we define A11 to be that first entry, A12, A13, all the way to A1n, because there's n columns here. And we have A21, A22, A23, all the way to A2n, again, because there's n columns. And we're down to the mth row, AM1, M2, M3, all the way to AMN, because there's m rows. We call the dimension m times n. So, if we're given a linear system, 2x minus y equals 5, x plus 4y equals 7, we can convert that into a matrix, an augmented matrix that looks like this. What we do is we take the numerical coefficients and we write them into a matrix of this form. So 2, -1, 5, 1, 4, and 7. So that's the augmented matrix based upon this linear system. Now, because we have some rules that we have for linear systems, we can also apply those to matrices. So we'll have some elementary row operations. We'll have 3 of them that we can go ahead and perform. The first thing is we can add a multiple of a row to another row. Okay, so that's our first thing that we can do. We can add a multiple of a row to another row. The second one is we can multiply any row by a non-zero constant. Okay, we can multiply any row by a non-zero constant. We can't multiply by 0 because if we multiply both things by 0, we get 0 equals 0, no good. Okay, the last thing is we can interchange any 2 rows, okay, which means we just put rows in different order. Okay. So those are the elementary row operations that we have for matrices. What we're going to look at next is an example of given a matrix, or given a linear system, converting it to a matrix, and solving that matrix. Okay, similarly how we solved systems of equations by getting rid of variables by using the process of elimination, we're going to do that same idea just using matrices, because what that does is it saves us a lot of time writing x's and y's and z's and that type of thing. So we have those rules that we can use. First, we can convert this to a matrix. Okay. So once we have a matrix, what we're going to do is we're going to use some of those row operations to get it in that triangular form. So the first thing I'm going to do is I'm going to multiply, this is called row 1, row 2, row 3, multiply row 1 by -2 and add it to this, and multiply row 1 by -4 and add it to this. And what that will do is give me zeros for here and here. Now the way I notate this is I'm going to do this. I'm going to go -2 times row 1 plus row 2. That's one thing I'm going to do. The other one is I'm going to do -4 times row 1 plus row 3. Okay, this is the notation I have. Okay, so that brings me to a matrix up here. My first line will stay the same, 1, 1, 1, and 2, right? First line is the same. But I'll do -2 times this plus this, that makes that entry a 0. -2 times this, -2 plus this is -5. -2 times this plus this makes this 0. -2 times this is -4 plus this makes this 0. Okay? -4 times row 1 is equal to 0, or row 1 times, -4 times row 1 plus this is 0. -4 times this plus this is -3. -4 times this plus this is -7. And -4 times this plus this is -7 also. Okay. All right. Okay, now that I'm here, what I want to do is I want to get that triangular form. One of the things I can do is I can divide this row. You can multiply or divide any row by a given number. I'm going to divide this row by -5. So I'm going to do this. I'm going to go row 2 divided by -5. Okay, and you can say it a lot of the ways. You could also write this as, you know, -1/5 times R2. I don't care the way you say it. It doesn't matter to me. So that gives us a new matrix. 1, 1, 1, 2, 0, 1, 0, 0. Because if I divide this by -5, this by -5, this by -5, this by -5, this is what I get. Keep this one the same. Okay. Now, I want to make this a 0. So I'm going to use this one, not this one, but this one, this row 2. I'm going to multiply it by 3, because when I add down to this, it'll make it 0. Now, someone person might ask, why can't you multiply this one by 3? Well, because then you'll get a non-zero entry here, and we want this to be 0. Because if I multiply this by 3 and add it here, I'll get 3, which is no good. I want to keep that to be 0. So I will multiply row 2 times 3, now it's row 3. So row 2, 3 times that, plus row 3. If I do that, I will get, keep my top row the same, second row the same, multiply by 3 out of this, get 0. Multiply by 3 out of this, get 0. Multiply by 3, get 0, add to this, -7. Multiply by 3, add to this, get -7. Okay. And lastly, I'm going to divide this row, every single term, or multiply this row by -1/7. Multiply everybody by -1/7, or divide it by 7, same thing. So I'm going to take this row 3, you have -1/7 times row 3, and that will yield 1, 1, 1, 2, 0, 1, 0, 0, 0, 0, 1, 1. Now, if I take this matrix and I convert it back to a linear system, the linear system it becomes is x plus y plus z equals 2, y equals 0, and z equals 1. And I think from here we can see that, hey, if y equals 0 and z equals 1, is it possible to figure out what x is? Yes, plug in y equals 0 here, plug in z equals 1 here. It turns out x will be the number 1, so I'll have 1, 0, 1 as my solution. Row echelon form and reduced row echelon form of matrix. So the first one we're going to talk about is row echelon form. So we just did an example. This one is now in what we call row echelon form. Row echelon form. Why? A matrix is in row echelon form if the first non-zero number in each row is 1. What's the first non-zero number? 1. What's the first non-zero number? 1. What's the first non-zero number? 1. So that has to be the first non-zero number. It has to be a 1. That's called the leading entry. The leading entry we want to be 1. The leading entry in each row is to the right of the leading entry in the row right above it. So we go 1, and we have the leading entry is now a 1, and it's to the right of the 1 before it, to the right of the 1 above it. Okay, and we have that, and then all rows consisting of entirely zeros at the bottom of the matrix. We don't have that in this situation. We do not have entirely zeros in that situation. Okay, so this guy right here is in row echelon form. Now let's take a look at reduced row echelon form. Okay, we talked about row echelon form. Now we want to talk about reduced row echelon form. So reduced row echelon form means, number 1, it's in row echelon form, and number 2, every number above and below the leading entry is a 0. So I need leading entry above and below 0, below 0. Is above and below 0? Below 0, but above is not a 0. Is every number above and below? Below, don't have to worry about. Above, it's not a 0. So we need to make that guy and that guy a 0. Okay, to be in reduced row echelon form. So first thing I'm going to do is I'm going to multiply -1 times row 2 plus row 1. Okay, what will that do? That will give me 0, 1, 0, 0, 0, 0, 1, 1. Multiply this by negative 1 out of that, get 1, get 0, get 1, get 2. Good. That's taken care of above and below. Above and below. Need to be above. This leading entry needs to be a 0. So what do? Multiply row 3 times negative 1. And now it's row 1. And what does that give me? So I'll have 0, 1, 0, 0, 0, 0, 1, 1. And if I multiply this by negative 1 times this, get 1. Negative 1 times this plus this, get 0. Negative 1 times this plus this, get 0. Negative 1 times this plus this, get 1. Okay. Now this is in reduced row echelon form. Now you'll note something about this. If something is in reduced row echelon form, you don't have to substitute back into the original system to be able to solve it. Because look, what does z have to equal? 1. What does y have to equal? 0. What does x have to equal? 1. So having it in reduced row echelon form definitely saves time.